Hello everyone! Today we're going to look at the mysterious and useful tool that is Green's theorem. In this first video, we will look at the statement itself, the intuition behind the theorem, and the conditions under which we can apply it.
So to begin with, let's suppose that you are given a curve that looks like this, a closed curve, and with its curve as C and enclosed area as D. And we want to calculate the line integral of this function, but sometimes it can be very difficult to integrate over this irregular curve C. So now there's something called the Green's theorem, which we can implement to convert the integration from a curve to the integration of the area D, which can oftentimes be easier. So what is the Green's theorem? So the Green's theorem states that if there's a function of the integral of a function that can be written as the integral of p dx plus q dy, where p and q are functions of x and y, this line integral can be converted to the double integral of the curl, aka the partial derivative of q with respect to x and the partial derivative of p with respect to y, taken over the area of the region. So the Green's theorem gives the relationship between a line integral around a simple closed curve C and the double integral over the plane region D bounded by C.
So another way to see this is by looking at this part, which is the curl. So here we have a closed curve, and here around it is the circulation. And the vector field is usually the source of circulation, which is simply the amount of force that pushes along the path. So it's basically the work. And then curl, as we've seen before, is simply the circulation per unit area, or the amount of twisting at a single point. So you can see that there. If you think of microcirculations in the region, they'll end up canceling each other out, so that the only circulation that really matters is the one that is on the outside. And this is what we can see through Green's theorem. Okay, so how do we get Green's theorem in the first place? I think it's easiest to look at a simple example where we are trying to find the line integral on this closed rectangle. And the circulation is going this way. And basically what you do is you take the p components and then you write them out like this. And amazingly enough, if you multiply by dy and divide by dy, it will obviously be equivalent, but it'll also give you the definition of the partial derivative of p with respect to y, and that times dy. And the same thing applies to q, the q components. You see that you have the definition of the partial derivative of q with respect to x times dx dy, and that's basically the form you get when you add them together. And voila, this is Green's theorem.
So what are the limits of the Green's theorem? So when can you apply this theorem to help you calculate? So first is that the curve C must be a simple closed curve. So by simple, it means that it never intercepts himself and it's not open. And second, C is positively oriented, which means that the interior is always to the left of the arrow as you move around. This is just a convention of how you calculate it in order to apply the formula. And what I mean positively oriented is that it goes counterclockwise. So the interior is always to the left of the arrow. And third is curve C is a piecewise smooth function and may have finite number of corners. The next one is that the vector field that we're differentiating in a line integral must be defined and differentiable in region D, which means that D has no holes in it, and D is conservative, and the vector field is conservative. And what is important to remember that Green's theorem only works on two-dimensional vector fields, so you should not try to apply it to the 3D when you see x, y, and z coordinates appearing all together in the question. You need to leave that to Stokes' theorem, which generalized to higher dimensions. So now you have learned about the definitions of the Green's theorem. Please watch part 2 of this video to learn some practice examples.